All right, we have an exam on SMCC is in lockdown. Okay, I did not know that. Thank you for sharing. I'm not sure why. Probably something unexpected happened. So I would imagine at some point too on campus, they'll start mandating people have to have some sort of lockdown training. We haven't had it yet for faculty, but at some point they'll do that. And the students, like, what do you do if there's an active shooting incident? I mean, it's happening more and more. And even though guns aren't legal on campus, you can't bring guns on campus. I'm not exactly sure how they get around the whole, what is that, the Second Amendment or the Fourth Amendment, but um, guns aren't allowed on campus. It doesn't mean you can't do a senior project that mimics a gun. We had this, I don't know, 10 years ago. We had a group that made a rail gun and they put it into a gun that looked like a Halo gun. Yeah. Yeah. So I guess it was lifelike enough that they asked the question to John Allen saying, hey, is this a problem with that? And then John came to me and I'm like, don't ask me. Let's go ask the chief of the UMaine police. And so they went there and the chief said, yeah, just for precautions, let's do this the safe way. So what they had to do was on the day of their presentation, because they were going to show it around, they had to go to the police department, check in with the police. The police escorted them in a police car with their senior project, which just looked, I guess, real enough that there was concern, escorted them to the building where they were doing their senior project presentation, waited outside while they did their senior project presentation. And then when they were done with their presentation, they got back in the car with the senior project, went back to the police station, and no incidents, no problems. But I can remember John asking me, like, hey, what should we be doing? It's like, I'm not an expert. Like, let's talk to the security experts. And it was a good thing because, who never know? You know what I mean? We don't want the police to be on edge. We don't want any other students to be on edge. So if the police are aware of it up front, and they were really cool about it, they're like, oh yeah, just bring it up here and we'll give you a ride. No problem. What time is it? It worked beautiful. But that's just the type of thing that you have to be prepared for in today's age. But speaking of prepared, this is the best thing you can do to prepare for pretty much most of the stuff until probably maybe in a couple weeks will actually exceed the material. But this is the book that I would have recommended if I was teaching 111 and 112 or 312, sorry. But there are a lot of really good practice problems with some basic theory. It's not intended to replace the class or the Boylstat book. It's just intended to give you a touch of the theory and then also some problems, lots and lots and lots of problems. So if you want some additional practice between now and the exam, which is this Friday during lab, right? You're allowed one note card, so a standard size note card. And you can use your calculator or MATLAB, right? Not and, but or one or the other. And I would just use this as a good study guide. So ECE made a Riley gun this year. Yeah, a rail gun, same thing, like you have the concerns about it. But this is like a really good study guide, going through the material, looking through the presentations. But if you want more practice, this is really good. I did put together a little document with some practice problems. But this is pretty high level because it's just a review, right? So we can go through these topics fairly quickly, not getting into a lot of detail. But even at the number one, use the outline series for electric circuits to get practice problems, tons and tons of practice problems with solutions and answers and or solutions. We started off with unit conversion way back, in the first week of classes. And the base units we had are joules, coulombs, and then from there, we can get voltage, current, and work and energy are just specific parts of that, right? Because work is power, but energy is typically joules or could be kilowatt hours. We haven't really covered under this first exam any other elements other than resistors that are passive elements, right? So you don't have to worry about time constants or any of that stuff. We'll pick that up in the next class. But you do need to think about what does all that mean in terms of having ideal resistors. And we've only assumed linear resistors. There are some cases when you do nonlinear, but for this class, we're just going to assume linear resistors. Then the only active elements that we talked about are independent and dependent power sources. And if you have a dependent source, normally all you need to do, don't panic, just write one additional equation. So I put that in as a highlight because, again, a lot of people, when they see dependent sources, get really, really nervous. You don't need to get nervous. You just need to write that additional equation. Non-ideal and ideal sources. Remember, an ideal sources can deliver as much voltage and or current as necessary to whatever circuit you connect to it. So that value, either the voltage or current, is a fixed value. Okay. So what we deal with in all your circuit analysis is we do have an ideal voltage or current source, but in reality, in the real world, there's no such thing. And so what we do is we add on internal impedances or equivalent resistors to go ahead and make our circuits actually act, our schematic circuits act like they do in the real world. So if you remember, if it's an ideal voltage source, it can provide whatever voltage you need, regardless of the current. If it's an actual, right, if it's a real world one, then what we saw is the voltage starts to drop as the current increases. So you put a resistor in series with your ideal voltage source to schematically represent a real world voltage source. Current is the opposite, right? The ideal current source should be able to generate whatever voltage you need, regardless of the demand for it. But we know that that's not necessarily the case. So what we do is as we increase the voltage, we actually get less current out of the system. And so that's why we have to put a resistor in parallel with our ideal current source and not in series. And those two, the equivalent internal impedances, are really helpful for telling us when we turn them off. When we turn off a voltage source, we shut the voltage source off, right? And we force it to be a short circuit or its internal equivalent impedance. If we shut off a current source, it's the same thing. We make sure there's no current coming out. So its internal equivalent impedance in that case is an open circuit. So if you want to go ahead and solve for Thevenin or do superposition, you would go ahead and turn those off by replacing them with their internal equivalent impedances. We then move to Kirchhoff's voltage law and Kirchhoff's current law. I don't know if I've convinced you all yet, but KCL is the way to go because generally speaking, you have less equations to solve, right? KVL, you have to do loops. So every time you have a loop, you've got to write an equation. Where KCL, you only have to do that if you have nodes. And a lot more stuff is in parallel in the real world than it is in the series. So KVL is the sum of the voltage drops around a closed loop equals 0. KCL is the sum of the currents into the node equals the sum of the currents out of the node. Okay, that's the way we've been doing them in this class. But again, you can do whatever you want. You're going to end up with the same solution. When we also move to multiple resistors, and we can figure out how to add those or determine equivalency with resistors either in series or in parallel. Resistors in series, just add them up, and that's all determined from KVL. Resistors in parallel, we determined that you would do the product over the sum, or 1 over plus 1 over plus 1 over and invert at the end. That's how you would do resistors in parallel. And how you solve for that is using KCL to solve for that equation. We had specific applications of KVL and KCL to very simplified circuits. And then if we had those simplified circuits, we could do current or voltage dividers. A current divider is using KCL for one and one only unknown node. The other node is reference, but you have only one unknown node. Then if you have 10,000 elements in parallel, you can use current divider to solve for any current in any branch off that node. But it has to be one unknown node voltage. KVL allows us to solve for voltage divider. And to make that work, our very specific circuit is we have a voltage source and we have a bunch of resistors in series. They have to be in series because the current through those has to be the loop current that we use in our KVL. And if you do that, then you can solve for any voltage drop across any single resistor just by using voltage divider rule, okay? So very efficient. You don't need to do KVL and KCL. I mean, you don't need to do voltage and current divider. You can always go back and apply KVL and KCL to get the answers that you want. We did application of KVL to get mesh analysis, and that just is some of the voltage drops around a closed loop equals 0. Then we introduced the concept of a mesh current or a loop current and a branch current, right? So a loop current lives entirely in that closed loop. A branch current is the actual current that flows through an element. And you might have multiple loop currents flowing through an element because of the way you've set that up. So, sorry, I can't talk too well. But yeah, you're just doing KVL, which means if you have a current source, you have no way of knowing what that voltage drop across that current source is. So you apply the super mesh concept, which really means all you do is you short circuit that current source. No, let's see, for KVL, we're looking for the voltage drops. So we would actually open circuit it, and then we would look for the voltage across that element. Okay, so that's the super mesh concept. And when we did nodal analysis, we just applied KCL, and all you needed to do was solve for the current flows into a particular node. If you had a case where you had an ideal voltage source or even a dependent voltage source, and there was no way to calculate what that voltage was, then you had to do the super node position, which means you shorted out the currents, the voltage source, and then you went in and actually used the rest of the circuit that was connected to determine what that actual current is. So you're just kind of stealing that information to do that. In both super mesh and super node, you got to write one additional equation, and that additional equation is based on the source that you took out. As long as you get the difference in mesh currents or the difference in nodal voltages, you can go ahead and solve for it that way. Then we talked a lot about Thevenin and Norton equivalents, and those are really just to make our life a lot easier from an analysis perspective. And it's for more advanced applications, right? So we will look at Thevenin and Norton when we're trying to go to advanced topics and theories, because for the most part, we're not going to build a circuit that's a Thevenin equivalent. We might as well just build our original circuit because that's the one that's doing something useful for us. But if we're trying to analyze a system and trying to find out some general information about it, doing Thevenin and Norton. Thevenin is the open circuit voltage in series with the equivalent resistance seen at the terminals of interest. Norton is a current source, short circuit current source, and that same resistance that we calculated for Thevenin, but the two elements are in parallel with each other. And then I think the last topic we covered was max power transfer, which says to find max power transfer for a system, your source impedance has to match your load impedance. And I'm not going to expect you to do the derivation. Remember the one that we put up on the board? That just takes a lot of work, so there's no reason to do that. So any question on those topics? Anything new or frightening? Haven't seen it. Hopefully it's all stuff that you've seen even before coming here into this class. Nothing? Okay, well, let's take a look at some examples. And these are right out of Shomes. Sorry for the poor resolution. But I've got to solve for V1 and V2 for this circuit. So any ideas? How would you solve this problem? Any thoughts? Any preferences? Yeah, I think this one might be easiest to do nodal analysis, right? Because if we had to do mesh analysis, we might end up with an additional calculation. So we know that this is the V1 node. I'm not even going to call this V2. I'm going to call that 105 volts, right? Because we already know what that voltage is. And this one is going to be V2. Whoops, somebody has a chat. Start with REQ equals 36 and parallel 12. Yeah, we can do that, but let's do the full Monty, right? Let's just go ahead and do full Monty so we don't have to make any simplifications. But that would certainly make a simplification if we did that. And here's the thing. We could certainly add a V3 over here if we want. It's up to you. Do we want to make that a V3, or do we want to solve for the voltage V2? We should actually call that V3 from here to here, and then solve for V2 doing a voltage divider. Totally up to you.
Why would you use branches? I thought, like, it did that whole right side of the branch.
Well, I'm looking just at the nodes, right? So I'm just identifying nodes. So I'm not doing branches. It's where two or more elements meet at a common point. Yeah. So I have a node right here, a node here, a node here, and technically I have one more right here other than the reference. But what I'm asking is, do we want to combine those resistors and make our work a little bit easier? Or do we want to add a third node there that we have to solve for? Any preferences? Third node? Okay.
Making work a little easier, maybe?
Make the work. Well, somebody already said third node, so we'll call this V4. How's that? Okay, so let's start. So we're going to assume currents. And I'm just picking these directions sort of haphazardly. Doesn't really matter. So the first one I'm going to do is the current into the node, V1. I actually have no current into the node, right? So that's going to be 0 current into the node. It's going to be all equal to current out of the node. So V1 divided by 36 plus V1 divided by 12 plus V1 minus 105 divided by 74. That's my first node equation that I need to write. I don't have to write one at the 105 because I know what the voltage is, so there's no work in doing that. So now I'm going to go over to V3, and the current into the node is 105 minus V3 divided by 16.4. That's current into the node. And I only have one current out of the node. That's V3 minus V4 over 103.2. And that's it. That's my current there. My last one is for the node V4. So my current into the node is V3 minus V4 divided by 103.2. And that's going to equal current out of the node, V4 divided by 28.7. Okay. Now let's check. How many unknowns? V1, V3, and V4. And I've got 3 equations, so I'm good to go. But I'm going to get a little sneaky because I actually want V2. So I'm going to add my third equation, and V2 is going to be equal to V3, or fourth equation, I should say, minus V4. So I added one additional equation to very quickly give me the result. It'll actually spit out in my matrix. So now I just got to go ahead and set up my system. So I have 104 divided by 74 equals V1 times 1 over 36 plus 1 over 12 plus 1, whoops, what happened? Plus 1 over 74. There are no V2s, there are no V3s, and there are no V4s. So I'm just cleaning these equations up so that I can set them in my matrix. Now I'm going to move to my second equation. So I can see that 105 divided by 16.4 is going to be equal to V3 times 1/16.4 plus 1/103. Actually, you know what? I'm going to line these up too. So let me erase these and move these over a little bit. So I've got no V1s plus no V2s. Now I have a V3. So that's 1/16.4 plus 1/103.2. And I've got no V4. So that's my second equation. My third equation, I got nothing over here. So I have no V1s, no V2s, plus V3 times -1/103.2 plus V4 times 1/103.2 plus 1/28.7. Last equation, 0 equals 0 V1 minus V2 plus V3 minus V4. So I got my four equations, my four unknowns. I dumped that into a matrix, and I've got my answer. Questions on that? Did I go too fast? The only thing that might have been a little bit interesting on this one is I wrote that last equation, that fourth equation. I didn't actually need to, but I know that I've got to at some point calculate V2. So I just threw it in here so I can get it all at once. Sometimes it's easier to put it in the equation. In this case, it probably wasn't any easier because now I got to add all those zero V2s and all these equations. But if you want to have it all in one fell package, you can just add it in there. That's the nice thing about the matrices. You can just keep adding equations over and over and over again.
Well, we didn't use MATLAB on my thing.
You can use a calculator or MATLAB. Yes, sir. You want to set it up in a matrix? Sure. So 105 divided by 74, 105 divided by 16.4, 0, 0 is going to be equal to 1/36 plus 1/12 plus 1/74. Then I've got 0, 0, and 0. That's my first equation. My second one is 0, 0, 1/16.4 plus 1/103.2 and 0. I'm going to go ahead and cheat because I'm running out of room that I can see everything. So my third equation, this is 0, -1/103.2 and 1/103.2 plus 1/28.7. And lastly, -1, +1, and -1. And that multiplies V1, V2, V3, and V4. Once you have them set up in sort of that nice clean form, where you have your unknowns on one side, your knowns on one side of the equation, and all your unknowns on the other side of the equation, and you kind of organize things. You just notice I just put V1, then V2, then V3, then V4. I try to lay that out in each equation, so then filling in the matrix is hopefully very efficient. Hopefully. Yeah, and you can use straight up voltage divider. You can use whatever you want. The only reason why I'm doing the full Monty way is that this works every single time. I don't have to guess and see things and combine things. But yeah, this works perfectly well. So there's many ways to skin a cat when you're doing circuit analysis, for sure. Because if you looked at this problem, right, you see that the 105 is across those three elements. So you could have just did voltage divider right off the bat, right? So if you want to do voltage divider here and solve for V2, that's going to be equal to 103.2 divided by 16.4 plus 103.2 plus 28.7. And then that multiplies by 105. By 105. You don't even need to do voltage nodal analysis. So we did the hard way, but we should get exactly the same results. Totally up to you. You get to decide. Question on the first problem. Move on to the second. No, yes. All right. Oop. So we are going to solve this one for I1 and I2. Okay. Well, this one's super easy because I1 equals 2 amps. Why even write an equation? I wouldn't. I wouldn't write an equation at all. And to solve for I2, I'm just going to focus on that loop right there, right? Just because I have that 5-volt, yada, 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 I'm not looking for the current through the 10 ohm resistor. I'm looking for the loop current I2. So I'm going to do the sum of the voltage drops going to be equal to 0. So I'm doing my I2 mesh. And what I see is minus to plus in the direction of current. That's a voltage rise. So that is plus 30 volts. Then I have a plus to minus voltage drop in that direction. So plus 6 times I2. And the same thing for the 4 ohm resistor. And that has to sum to 0. You will note there's no other mesh current flowing through there, right? There can be current flowing through here. That's not a mesh current, is it? That would be a branch current. So if I wanted to calculate the mesh current there, that'd be a lot more challenging because I'd have to go back through it. So all I'm going to get there is a potential difference, which would give me a current, but I can't apply a KVL with that connection there. So my I2 3 amps.
Did you start in the bottom right?
I started right here, bottom left.
Going up that pole, and it's the same polarity as the 6 I2. Would those be different polarities or?
Oh yeah, you're right. This has to be negative. I put positive. I did it right on the other side, but yes, that's a negative because it's a negative voltage drop, right? It's a rise. Question on that? So sometimes when you look at the circuit, right, and I put the circuit up there specifically because it's like, oh my God, what am I going to do? There's this weird interconnection between the two. So what? You can handle that. Now the question is, would current flow through them? And the answer is maybe, because you'd have to have some way for those two to be referenced to the same point, right? You've got to get current flow in there. Otherwise, there'd be no current flow between them because you wouldn't connect. So this 5-volt supply has to be tied to ground at some point, or else it's not going to work. But even then, that doesn't matter. You just kind of skip, the need for information there. Okay. Next problem. We're going to solve for I, the dependent source. You guys want 5 minutes to tackle this one on your own, or do you want to just show you how to do it? It's totally up to you. This is your review session, so I'm not trying to confuse you. I'm trying to give you, what I think would be good practice problems to set you up for the exam. But I don't want you to spin your wheels on stuff if you don't feel comfortable. That's why I'm willing. I don't expect you to actually work, because now this is just a review. We're not learning stuff. So it's totally up to you if you want to see me do it, or if you want to do it yourselves and then see me do it.
More for example, if you just went through it, that way, like for me, like after we've done this session, I'm just gonna look over it, and I have the opportunity to look at that, pause the video, try it myself, and then see how to get it.
Yeah, that's fine with me. I'll do whatever the majority of the class wants to do.
I like that. We can go back and watch these more than having some.
Yeah, sure. That is the advantage of watching the recording. I know you get to see me from a weird angle. It'd be better if there was a camera there, but the only other option is I could turn the camera off.
Not really looking.
Well, as I say, you want me to turn the camera off? Would that be a better way to do it? Because then it just has a blank screen.
Doesn't really make much difference.
In Zoom, you can actually turn off the camera, the presenter camera, right? So it just displays the screen.
Oh. But you look a little box.
It's a little box, yeah. Actually, you can't, because it's a YouTube video. It's not even a Zoom session.
Oh, right.
There would be a way that I could do it, but
It's not that.
okay. Well, the other thing would be a black box, but I kind of show, like, if we're in a live class and I'm actually interacting with students, I actually want to have my camera on, just like you would in a professional meeting. Because if you're in a meeting with 10 people and they're all on Zoom with their cameras off, are they paying attention? Are they not paying attention? It's hit or miss, right? So from a professionalism standpoint, I've been to many meetings where my camera is the only camera that's on. But, that's just how I perceive professionalism, and it's not a judgment. It's just, that's what I do. So, okay. So what do you want to do? Do you want to do mesh, nodal? Do you care? Nodal? Okay. Do you want to do some fast, like simplifications? Or do you want to just do like the full Monty version? Hack away? Is that the full Monty, or is that full Monty? Okay. I will ignore the fact that we know what that node voltage is, right? But we'll call this V1. We'll call this V2. We'll call this VR. And we can call that V4, but I think we'll just call it 3VR, right? We'll just call that 3VR just to make it easy, because we know that voltage with respect to reference is VR. And we'll start picking directions. So there's current here, and current here. Okay. All right. So our first current is our first nodal. We have current into the node, 2 equals current out of the node, V1 divided by 3. Our next node is our V2 node. So current into the node, there is none, 0, is equal to the current out of the node is 2 amps. We can't even say V2 minus V1, but we don't need to, because we know what the current is. So why do V2 minus V1 divided by something when you can just say it's 2 amps? So that's 2. And then plus, we'll assume that this current isn't down in this direction. So what are we going to do over here? How do you solve for that? Any ideas? Say that again?
V2 plus 4 over VR.
V2 plus 4 over VR.
Or 54.
You're sort of taking some shortcuts. So we're going to do our full Monty, which our full Monty says replace this with its internal equivalent impedance, which is a short. And now that current here has to be the same as that current, right? That's just VR divided by 2. Correct? So we just did the super node right there. Because we had a voltage source that we don't know how to deal with. But all we do is we short it out and we recognize that the current through the 4-volt source has to be the same as the current through the 2-ohm resistor, which is VR over 2. And that's
Are
it.
you using Supernode to analyze this one?
I had to use supernode, yes, because I had the 4-volt source, and there's no way of getting the current from the 4-volt source without doing some tricks. So the trick that I did was the supernode approach.
Okay.
Okay. All right, now we're going to do our next node. And it's going to be the same problem, right? So we have a voltage source here. Oh, but wait a minute, Paul. Why would I do that? Because we know that's 3VR. I don't need to do a nodal equation for the 3VR node. I know what the voltage is. It's 3VR. So that's not a nodal equation. That tells me that this node is in fact 3VR. So I could have called it V3, but I just called it 3VR. So I have 1, 2 equations, or 3 equations. But I don't really have what 3VR is equal to, right? So I've got 2 equations. How many unknowns? Oh, wait a minute. I screwed up. I actually forgot this current right here. That's V2 minus 3VR over 5. So I have 2 equations and V1, VR, and V2. I have 3 unknowns. So I have to write one additional equation. How would I write that additional equation? Any thoughts? Let me rewrite my equations a little cleaner. 2 equals V1 over 3. 0 equals 2 plus VR over 2 plus V2 minus 3VR over 5. And I'm not even going to really write my third equation there. So what do I do? What's my third equation that I'm going to write? V2 minus VR equals 4. Very good. Because normally I'd like to write an equation for the dependent source, but I can't really write one easily. But if I recognize a supernode, my third equation is V2 minus VR has to equal 4 volts. It's the potential difference between those two. So now I have 1, 2, 3 equations and 3 unknowns. So do you want to see me set these up so that they look like a convenient matrix? All right, so 2 equals V1 over 3 plus 0 V2 plus 0 VR is our first equation. Our second equation, -2 equals 0 V1 plus V2 over 5 plus VR times 1/2 minus 3 over 5. And my last equation, 4 equals 0 V1 plus V2 minus VR. Three equations, 3 unknowns. So this one was a double, right? we had a dependent source, and we had to do a super node. But really, the dependent source didn't add a lot of complexity to us, right? Because we labeled that node VR. That made it really much, much easier for us. If it was a current source, a dependent current source, then we would have to write one additional equation. But fortunately, because it was a voltage, it gave us the node, and we were good to go. Again, when you looked at this problem at the beginning, what did you think? Uh-oh, how do I start the problem? But then you look at it like, oh, it's really not that bad, I hope. Right? You're just seeing how a lot of this stuff shakes loose, and it's really not terribly challenging, hopefully. Okay. Any more discussion on this? Want to go to the next problem? Whoops, it's just the same problem. Did I not paste it in? Sorry about that. I had a Thevenin equivalent one. I'll show you where I went just to chapter 3. And it was towards the end, but I thought I pasted it in. I apologize for that. Let's see. Here, this problem right here. So let's delete that one. And let's go over here. And we're going to solve for the Thevenin equivalent circuit seen at terminals A and B. So immediately you got a problem here, right? You can't do series and parallel combinations because you have a dependent source in there, don't you? So you're stuck without having to, without being able to do any of that work. So you're going to have to pause. And so what I recommend on this one is we're going to redraw the circuit just a wee bit. 6, 4, 6, 2, 5, 2I, and my current that drives it is right there. Okay. So what do you suggest? I'll move the 6 over here. What approach would you do to solve for VAB? First off, did I redraw the circuit correctly? I just moved the 6 ohm resistor to make it a little more straightforward. Hopefully that you see it. But I hope I'm not being too sneaky, but what would you do for this particular problem? How would you do it? Any thoughts? Yeah, I would do mesh with one simplification. So we normally do this, so I'm not going to change those. I'll call that I1. I'll call that I2. So now I'm going to be really lazy. And I1 equals 2I1, isn't it? Negative 2I1.
I think the I is going through the
Oh, 6 ohm resistor. Yes, thank you. In this direction here. Yep. So I1 equals negative 2I, doesn't it? So I don't have any work to do there. I basically have the answer through there. Now I'm gonna go ahead and do my other loop. And so what I'm gonna do is I'm gonna start drawing my plus to minuses for all the mesh currents. Got them all. So now I'm gonna just sum the voltage drops so I can see that, let's see, I've got 6I2 plus 4I2 plus 6 plus 2I2, and then minus 2I1 goes in the opposite direction, is going to be equal to 0. Okay? Now, how many unknowns do I have? I1, I2, and I. So I have 3 unknowns, but only 2 equations. So I have to write one additional equation, and I'm going to do it for that dependent source. And that additional equation is going to be equal to, let's see, I is equal to negative I2. So I added a third equation, but I didn't add any unknowns. So now I can just go ahead and set this up. So I have 0 equals I1 plus 0 I2 minus 2 times I. My next equation is negative 6 is going to be equal to negative 2I1. So I got 6, 10, 12 plus 12I2 plus 0 times I. And my last equation is 0 equals 0I1 minus I2 minus I. If you want,
Paul,
yes.
if you don't mind, can you briefly just explain how you got the third equation real quick, please?
Yep. So I is right here, right? Going through the 6 ohm resistor. And I see that I have I2 going in the opposite direction, correct? So all I said was I is going to be equal to the negative of I2 because they are going in opposite directions.
Okay, thank you.
Yep. I might add a third equation. And my third equation, just if you ask me, this is VA to B. I can see that I want to get plus to minus here and plus to minus here. So to me, VAB is going to be equal to negative 6 times I2 plus 5 times I1. So I'm going to add one additional equation so I can just spit out, just spit out what my last equation is. So this is going to be equal to 0 equals 5I1 minus 6I2 plus 0I and then minus VAB. So I'm going to add in my fourth variable there. So I'm going to immediately spit out what my voltage is, what VAB is, what my Thevenin equivalent voltage is. So that's my B Thevenin is my VAB. Now I've got to do this circuit all over again, but now I have to put a short, right? Because I am looking for I Norton through terminals A and B. So this is 6. This is 5, 4, plus minus 6, I believe. 2. My dependent source, which was 2I, I believe, going in this direction. And my controlling current is the I over here. So I have to solve for IN, right? In this short circuit condition. So at this point, you can decide what you want to do, but I'm probably going to do the same thing I did before. Is 3 separate meshes because I've got a lot of nodes in here, right? I've got 1, 2, 3 nodes. And if I can write an equation for I1, I2, and I3, I see that I1 is equal to negative IN. So I don't have to do any additional work to pull out the equation. I can just grab it from there. So we'll do our same approach here. We'll add our pluses and minuses. Let's see, this is plus minus here and plus minus here and plus minus here. So I'm going to do my I1 loop. So I have, let's see, I have 6I1 plus 5I1 minus 6I2 minus 5I3 going to be equal to 0. That's my first equation. My second equation is, let's see, so I've got 6I2 plus 4I2 plus 2I2 minus 6I1 minus 2I3. And in the direction of I2, that becomes a positive 6, right? Because a 6-volt source is a voltage drop. Now for my last equation, I have 5I3 plus 2I3, and then minus 5I1 minus 2I2. And actually, no, wait a minute. I don't even need to do that. Make it much easier. I can see that I3 is going to be equal to negative 2 times I. So I've got 3 equations, but 4 unknowns. So I have to write one additional equation. Well, my additional equation is I is going to be equal to I1 minus I2. So now I put that in standard form. Let's see, I have 0, minus 6, 0, 0. And so I'm doing these a little faster because hopefully you're seeing what the process is. This is 11, minus 6, minus 5, and 0. And I'll put my variables here, I1, I2, I3, and I. So that's my first. My second equation, I've got, let's see, I've got 12I2 minus 6, a minus 2, and a 0. In my third equation, I've got no I1, I2. I've got 1 I3 and a negative 2 here. And over here, I have a 1 I1 minus I2, and then 1 there. So when I'm all said and done, Z or R Thevenin is VAB, or V Thevenin divided by I naught. So in my opinion, easily the hardest problem on this one was this last problem. And it was because you had that dependent source. So the dependent sources can mean a lot of additional work because we had to do the V Thevenin and I Norton on this one. There's no other easy way to go ahead and do it, except you could have also said, if this is a 1-volt source, measure the current out of there, and then you can calculate it that way. So that's the other option too. If that's seeming like it's a lot of work to get I Norton and V Thevenin, you can always go back and just put a test source. That works perfectly fine. Questions on that? Did I go too fast? Everybody was feeling good until we hit the 4th problem. Now you're like, oh, the energy gets sucked out of the room.
Quick question.
Yes.
Um, I think I know the answer, but I just wonder, you can't use superposition to solve that because of that dependent source. Is that correct?
That's exactly right. The definition of superposition is you turn off all linearly independent sources, right? And then solve for the contributions. So if you turned off all linearly independent sources and turned on one at a time, you basically would get this circuit that we did right here. And all that's going to give you is the voltage. You still need to solve for the current, right, to get the impedance, but superposition does not give you Thevenin equivalence. It'll give you a voltage, but it won't give you an impedance. So using superposition doesn't help you for doing any equivalent resistance calculations. Okay. Oh, did we lose Arthur?
No, no, thank you.
Okay, sure.
Got it. Thank you.
More questions on this one? Like I said, I didn't intend to drain the energy out of the room. I just wanted to show you, like, some of them can be more complicated.
So, where to? That analysis.
The one right up here, because we needed to solve for V Thevenin.
Oh.
We need to solve for the Thevenin equivalent, which means we need the open circuit voltage, and we need the open circuit or the equivalent circuit impedance. When you have a dependent source, you've got to solve for the Norton equivalent current and do it that way, or you've got to put a test voltage on there and do it that way. So anytime you see dependent sources, you got one of two ways. Thevenin and Norton, or dependent or test source, and find it that way.
So having both the Thevenin and the Norton.
Yes, because if you remember, here's my Thevenin equivalent circuit. Here is our Norton, so we'll call that V Thevenin. And from a terminal perspective, those have to be equivalent to each other, right? So from a terminal perspective, if I put a dead short circuit across here, I will get I Norton. And Ohm's law says I Norton equals V Thevenin divided by R Thevenin. So R Thevenin equals V Thevenin over I Norton. They have to be equivalent to each other. So that's how it teases out of it. Good? Other questions on this problem? I have to apologize because this is your review session and I'm taking it over, right? I've been yapping for an hour. The review session should be a opportunity for you to ask questions of me, not for me to put stuff up on the board. So I hope this wasn't a complete waste of time to go through this stuff.
No,
I always need to be a
sometimes,
little bit prepared, so.
no, sometimes working through these is very helpful. Thank you.
Is it? Okay. What questions do you have for me about the test?
I have a question.
Yes.
Is it gonna be like, I guess the questions on the exam, is it gonna be like how it is here where we kind of just picked like the method that we see like best fit, or are you gonna tell us to use?
I will have a couple problems where I will ask you to solve for mesh currents or solve for the node voltages. And that would mean generally you got to use mesh analysis or nodal analysis to do it. But if I don't tell you a method to apply, use whatever you want, whatever is the most convenient.
And then for the note card, is it just, it's like one of those little 3x5s?
Yes.
And
Yep.
then can we use the front and the back or just one side?
You can use both sides.
Cool, thank you.
Do you see why I give you a note card, not a full sheet of paper? Because there's nothing really to write down. You don't have any equations, right? I mean, you got Ohm's law, but everything else probably is burned in your brain at this point. So your note card, unless you put tons and tons of problems on there, it's not going to have a lot of information. And I can suggest if you put tons of problems on your note card, you will find that that's not a good way to study, because you're relying on, hey, here's this problem, and I have to be exactly like this problem to be able to apply it. So when you're taking a test, it's better to make sure you understand the concepts and how to apply them, as opposed to, okay, how do I solve problem A or B or C? That's generally a better way to do it, in my opinion. Yes, sir.
Any questions?
I think it's 6, I think. And you know, you have the full lab period, right? I will be there administering the tests.
So we should take it online. Do you have to print out the exam that morning and then do it like all on Bright State?
No, so to do if you want to do the exam online, you just need to use the, so I'll set up a video link for lab. And you'll log into that video link and you'll have your camera on showing your workspace. And you can leave the test on the screen, but you want to do work on paper. So you want to be able to, when you submit your test, be able to submit it by taking pictures of your submissions or scanning them in, whatever you have at your place. And then you got to get them up before the end of lab.
That's all.
I was gonna ask, I didn't know if you're gonna attach a file that we could
And your
print out.
completed results.
So you'll work with it.
Right. Some people like to print out the test. So it's, they prefer to have the test right there. Instead of looking at it on the screen. I don't have a particular preference. It's up to you. I've seen it go both ways.
I was just actually gonna ask if you were gonna drop a document we could print out.
Yeah, it's gonna be just like the homework where you'll have an assignment that'll be available at the beginning of lab. And then you'll just do the exam. You'll download it or print it, whatever you want to do. And then you'll take the exam on scratch paper and then you'll submit it at the end. So the thing is, it's gonna be neat and orderly. And the other thing too, is I told this to my other class, if you use MATLAB, I don't want to see you submit a MATLAB script file for your answers. Because I want to see all your work on scratch paper. If you just do script files, I don't know if you've generated them in advance. So MATLAB script files are not submissions. It's just a calculator. Would you submit all your hand, button pressing for your calculator if you were taking a test? No, you do all your work on paper and pencil, and then you just use your calculator input stuff, and then you get results. MATLAB should be the same way.
So we can just like draw the matrix like that and then just write the answer. We don't need to take a screenshot from MATLAB.
Would you do that with your calculator? Same deal.
Okay.
MATLAB is just a calculator. In this class, right? I'm not trying to see if you can write code. I'm just trying to show you that this is a really powerful, useful tool that makes your life, I think, a lot easier, and you can check your work. So if I was into these problems, I would do my work on paper. I would write a MATLAB script file to give me the answers that I'm looking for. And then when I go back and check my work, I can see if I entered anything incorrectly into MATLAB, just like in your calculator. The problem with your calculator, though, right, is you got to use the arrows and move up and down. Or with MATLAB, you can do that, but much more efficiently. But that's not mandatory. You can do calculator. Nothing that we've done here, as long as you can invert and multiply matrices, nothing we've done in here takes a really fancy, powerful calculator. Even the TI-36s in my other class can invert matrices, 3x3 matrices with complex numbers. So this should be able to do 4x4 because there are no complex numbers, I think. Other questions? No questions? We're gonna start, we'll finish up the capacitors and inductor stuff, and then we'll start on new material. But if you have a few questions for the test, it's not gonna be a full session of review. If you have any specific questions, then we'll go over those, but we won't spend, this is almost an hour now. Over an hour, right? We've spent an hour and 5 minutes doing this, so. Yeah, this class is dedicated to just going through the tests and what I think you need to prepare. It's a review of a review, right? Because the first month we've just been reviewing material. Again, I'd keep going, albeit at probably a much faster pace than what you've seen at your previous works, but that's okay because it's a review. None of this stuff is probably new. All right, any questions from TV land or? You have a question, Luke? Well, you can ask if the class doesn't.
How do you write natural log?
MATLAB? Sorry. Log. If you want to go log base 10, you got to type in log 10. So we talk normally about natural log, we say ln, but in MATLAB, log means ln. And log 10 is 10 base log. So you just type in log. That's natural log. Okay, any other questions? Get 9 minutes. Don't need it. Don't want it.
I do remember that quirk about it defaulting to the natural log for MATLAB. And EXP is a natural exponent E, correct?
Yes, you can't. I put an E and then I realized that's a mistake. But you can in MATLAB, if you want to just use the symbols, you can say E equals EXP of 1, right?
Yeah,
So now if you do the log of E,
yeah, you can define variables for whatever you want. It doesn't really care.
yep. But when I first did log of E, it burped, right? It didn't like it. So if you want to just do E to whatever power, you can just go EXP1, and then I just define it equal to E. MATLAB tries to reserve a lot of variable names, but like pi, it's reserved for itself. I or J are previously reserved. But other than that, there's not many predefined variables in MATLAB. The obvious ones, like I said, I, J, and pi, they need to be defined as actual numbers. But all the other variables that I can think of, except for maybe Avogadro's number or something like that, but I don't even think that's so specific that I don't even think we do it. So
Have you experimented with some of these problems in using Python?
no, I'm too old for Python. No, I'm kidding. Python is similar to MATLAB. It's a scripting language, but I'm not trying to teach you guys how to be programmers. This is not the intent of this class. The intent of this class is just to be able to learn, circuit analysis essentially. And so how I think it works best is to use MATLAB as your calculator. Mainly because you can see me do it, right? You can see how I enter it in, and you can see, okay, well, that's how it's entered in. I can do that. As opposed to just spitting out the results, I find it's more helpful to actually see what that is. So I'm not actually helping you or trying to teach you how to write code. Maybe a little bit more next semester or next year when you do some classes, because you do have to do some while and if loops, but really simple, basic stuff. These are definitely not intended to be coding classes. So that's why I don't do Python scripting.
The reason that I brought that up is because it reserves J for the imaginary unit and it does not recognize I, which clearly means that library was designed and intended for electrical engineers.
Yeah, probably, yeah. But you could always define I up front for something like that, unless it's again reserved for a function call. There's also a freebie one. If you don't like MATLAB, if you want to use when you graduate,
One of the reasons I think in Python J is reserved because generally we use for I in range of blah and then use that to, iterate a loop.
okay.
That's kind of convention. That could be one way too. But yeah, there's a lot of people in Stack Exchange that debate, why did they use J? I was like, well, if you're an EE or EET major, you'd understand that.
Yeah, I is reserved for current. So yeah, that makes sense. I said Ovation. It's actually Octave is the program that some people use, but it can be a little bit quirky. So while you're here on campus, use MATLAB for free. When you get out in industry, if you want to buy it, $6,000.
Ouch.
What's that? Stick with the calculator. But like I said, I mean, I've done stuff in industry where I've worked for companies and I've used MATLAB, their professional license, because you're trying to do some complex calculations and you got to use a software package to do it. I mean, you can try to do it on your calculator, but if you make a mistake, it's really difficult. You can do a lot of calculations in Excel, but the problem with Excel is Excel doesn't work well with complex numbers. For MATLAB, it doesn't, no problem. And I can also write loops. So if I had to generate many, many points, like in a plot, easy peasy in MATLAB. But to do it in Excel, you have to keep copying cells over. It's much more arcane and difficult to do that in Excel. But that's not Excel's purpose, right? That's not where its strong suit is.
Nope.
But that's MATLAB's. So MATLAB can do that really well.
If you want to really save money, I would really recommend you learn Python because it's free. And it does
Good.
complex numbers.
How
And
much
it's
does it cost?
huh?
How much does it cost?
It's nothing.
Okay, yeah.
No, you just go to the python.org and you just download the package and you can use it in whatever editor you want, VS Code or even its built-in command line interface, whatever.
Yeah, I got to start playing with Python. But here's the actual cost for MATLAB. If you didn't want all those additional add-ins, it's $1,000. Still not cheap, but
That's actually not a bad deal for what you get with MATLAB. That's to me worth it.
oh, I agree. But again, I like using MATLAB a lot. So, okay, any other questions? All right, y'all have a great day. I will see you on Thursday. Take care, everyone.
All right, thank you
you,
very
Paul.